Welcome! In this session, we'll explore an exciting coding problem from LeetCode, number 1196, titled How Many Apples Can You Put into the Basket? Together, we'll break down the problem, analyze potential approaches, and discuss how to arrive at an optimal solution. Let's dive right in. In this problem, you are given a basket that can hold a maximum weight of 5,000 units, and you need to figure out how many apples can be placed in the basket without exceeding this weight limit. Each apple's weight is provided in a list called weights, where weights, I, represents the weight of the ith apple. The challenge is to calculate the maximum number of apples that can fit inside the basket under this constraint. The input to the problem is the list of apple weights, and the output is an integer representing the maximum number of apples that can be added to the basket without surpassing the total weight limit of 5,000 units. For example, if the input list of weights is 100, 200, 150, 1000, the total weight of these apples is 100 plus 200 plus 150 plus 1000 equals 1450, which is well below the basket's weight capacity of 5000. This means all 4 apples can fit into the basket, so the output in this case would be 4. In another example, with the input 900, 950, 800, 1000, 700, 800, the goal is to fit as many apples as possible without exceeding the weight limit. The optimal approach involves sorting the weights and adding the lightest apples first to maximize the count. When you do this, you can fit 5 apples before exceeding the limit, so the output is 5. Let's break down the second example in detail. The weights of the apples are 900, 950, 800, 1000, 700, 800. First, we sort the weights into ascending order to prioritize lighter apples, 700, 800, 800, 900, 950, 1000. Then, we start adding apples one by one while keeping track of the total weight. Adding 700 brings the total to 700, then adding 800 raises it to 1500. Adding another 800 makes it 2,300, and including 900 brings the total to 3,200. Adding 950 takes the total to 4,150. At this point, adding the next apple, which weighs 1,000, would bring the total to 5,150, which exceeds the weight limit of 5,000. Therefore, we stop here, and the maximum number of apples we can fit is 5. As a result, the output is 5. Now, consider the third example where the input is 5,000, 5,000. Here, each apple weighs 5,000, which is equal to the basket's total weight capacity. However, the problem specifies that the basket cannot exceed its limit, so even a single apple cannot be added without going over. This means that no apples can be placed in the basket, and the output is 0. To summarize, the key to solving this problem is to sort the weights in ascending order and add the lightest apples first, ensuring that the total weight remains within the basket's capacity. Be mindful of edge cases such as apples that individually exceed the weight limit, or scenarios where the basket is exactly filled to its maximum capacity. The constraints ensure that the weights list will contain between 1 and 1000 apples, and each apple's weight will be between 1 and 1000 units. To solve the problem of determining how many apples can fit into a basket without exceeding a weight limit of 5,000, we first consider the brute force approach. This method involves generating all possible subsets of apples and checking the total weight of each subset. For valid subsets, meaning those with a total weight less than or equal to 5,000, we calculate the number of apples and track the maximum count across all valid options. The downside of this approach is its computational expense. It requires evaluating 2 to the power of n subsets, which becomes impractical for larger input sizes, such as when n exceeds 20. This leads us to a more efficient alternative, the greedy approach. Here, the intuition is to sort the apple weights in ascending order so that we can prioritize adding the lightest apples first. By doing so, we maximize the number of apples before reaching the weight limit. The process involves sorting the weights, iterating through them, and adding apples to the basket until the total weight exceeds the limit. This strategy is efficient because it avoids unnecessary calculations, focusing only on the most promising additions. By stopping as soon as the weight limit is crossed, we ensure that no heavier apples are considered unnecessarily. Another interesting solution to this problem is to combine the idea of sorting with a prefix sum and binary search. After sorting the weights in ascending order, the prefix sum is calculated, which helps us pre-compute the cumulative weight for different numbers of apples. Using this prefix sum array, we can apply binary search to quickly determine the largest number of apples that can be included without exceeding the 5,000 weight limit. The prefix sum allows us to efficiently check the cumulative weight for any given number of apples, while binary search reduces the number of checks needed to find the optimal count. This approach is faster in terms of determining the valid number of apples for larger inputs, but it does come with a trade-off. It requires additional memory to store the prefix sums. While this method is efficient in certain scenarios, the space overhead may not always be ideal. After evaluating the different strategies, the greedy approach emerges as the best choice for this problem. Its simplicity and efficiency make it highly suitable, especially given the constraints. Sorting the weights takes n log n time, and iterating through the sorted list to add apples requires n, resulting in an overall time complexity of n log n. This is optimal for input sizes up to 10 to the power of 4. Additionally, the greedy method avoids the space overhead associated with the prefix sum approach, making it more memory efficient. Comparing the options, the brute force method is clearly impractical due to its exponential time complexity, while the binary search with prefix sum adds unnecessary memory usage. The greedy approach strikes the right balance between time and space efficiency, making it the most effective and straightforward solution. Its alignment with the problem's constraints ensures that we can solve it optimally without overcomplicating the implementation. To solve this problem, we need to determine the maximum number of apples we can include in a basket without exceeding a total weight limit of 5,000 units. The weights of the apples are provided in an array, and our task is to identify the largest possible subset of these apples that meets the weight constraint. A straightforward way to approach this is through a brute force method. First, we interpret the input. The array weights of size n contains the weight of each apple, and our goal is to maximize the number of apples in a subset while keeping the total weight within the limit. Next, we generate all possible subsets of apples. For an array of size n, there are 2 n subsets to consider, including the empty subset. To efficiently generate these subsets, we use bit masking, where each integer mask from 0 to 2 n 1 represents a subset. The binary representation of the mask indicates which apples are included. For instance, if the binary of the mask is 101, this means the subset includes the first and third apples. Once we've generated all subsets, we evaluate each one by summing the weights of the included apples and counting how many apples are in the subset. If the total weight of a subset is within the limit, we check if the number of apples is greater than the current maximum count. The result is the maximum number of apples that can be selected without exceeding the weight limit. The next step in our brute force approach is to evaluate all possible subsets systematically. For each subset, represented by its bit mask, we calculate the total weight by summing the weights of the apples included in that subset. This is determined by checking which bits are set to 1 in the mask. We also count the number of apples in the subset during this process. If the total weight of the subset is less than or equal to 5,000, we compare the count of apples in this subset to the current maximum count. If it's higher, we update the maximum. After iterating through all subsets, the result is the maximum number of apples that satisfy the weight constraint. The pseudocode provided clearly illustrates the steps. We loop through all 2 n subsets using the range 0 to 1n. For each mask, we initialize variables to track the total weight and apple count, and then iterate through the array to determine which apples are included. If the calculated weight is within the limit, we update the maximum count accordingly. This brute force method ensures that we explore all possibilities, but as the size of the input n increases, the exponential growth in the number of subsets makes this approach computationally expensive. While the brute force method guarantees accuracy, it is highly inefficient as the number of subsets grows exponentially with the size of the input. Specifically, the time complexity of this approach is 2 to the power of n*n, where n is the number of apples. This makes it impractical for larger arrays, such as when n exceeds 20. To address this limitation, we can explore more efficient strategies, such as greedy algorithms or dynamic programming. One key observation is that lighter apples are more likely to maximize the count without exceeding the weight limit. This insight leads to the idea of sorting the apples by weight, which forms the basis of a greedy approach. Additionally, the problem structure has similarities to the knapsack problem, where dynamic programming can be applied to find an optimal solution. To summarize, while brute force is useful for small inputs and understanding the problem, its inefficiency drives the need for alternative methods. In terms of data structures, the array weights is central for storing the apple weights, and bitmasking is utilized to represent subsets compactly. For example, the binary representation of a mask like 101 corresponds to selecting the first and third apples in the subset. To overcome the inefficiencies of brute force, we can use either a greedy or a dynamic programming approach. In the greedy method, we first sort the weights in non-decreasing order. This ensures that we prioritize lighter apples, which allows us to maximize the count while keeping the total weight within the limit. We then iterate through the sorted list, adding apples to the subset until the total weight exceeds 5,000. The time complexity of this approach is O, n log n, for sorting, plus O, n, for summing the weights, making it significantly faster than brute force. Alternatively, we can apply dynamic programming, which is a more sophisticated yet efficient method. Here, we define dp, w, as the maximum number of apples that can be selected with a total weight exactly equal to w, and we iteratively update this array. For each apple, we look at all possible weights from 50-100 down to the apple's weight, updating the maximum count based on whether including the current apple results in a better solution. This approach has a time complexity of O, n asterisk w, where w is the weight limit, which is 5,000 in this case. Ultimately, the choice of approach depends on the problem constraints. Greedy is faster and simpler, while dynamic programming guarantees an optimal solution. This solution for LeetCode problem number 1196, how many apples can you put into the basket, officially calculates the maximum number of apples that can fit into a basket with a weight limit of 5,000 units. Here's how the code works step by step. 1. Sorting the weights. The first step is to sort the array of apple weights in ascending order. This ensures that we prioritize adding lighter apples first, maximizing the total number of apples that can fit within the weight constraint. 2. Initialization of variables. Two variables are initialized to keep track of the total weight, total_weight, of apples added to the basket and the count, of apples that fit. Both start at 0. 3. Iterating through the weights. Using a for loop, the code iterates through the sorted list of weights. For each apple's weight, it checks whether adding the current apple would exceed the weight limit of 5,000 units. For breaking the loop, if adding the current apple's weight would exceed the limit, the loop breaks immediately. This is an optimization to stop unnecessary iterations once the basket is full. 5. Updating total weight and count. If the apple can be added without exceeding the limit, its weight is added to total_weight, and the count is incremented by 1. 6. Returning the result. After the loop completes, either because all apples have been considered or the basket is full, the function returns the count, representing the maximum number of apples that can fit in the basket. This approach has a time complexity of O, n log n, due to the sorting step and a space complexity of O, 1, making it efficient for the problem constraints. The algorithm handles edge cases gracefully, such as an empty list or when no apples can fit within the weight limit, returning 0 in such scenarios. Here, we begin our Java implementation of the solution. First, we import the necessary utility classes and define the solution class. Within this class, we have our method maxNumberOfApples, which takes an array of integers called weight as input. This array represents the weights of the apples. The first step inside the method is to sort the array in ascending order using the arrays.sort method. Sorting the weights ensures that we can process the lightest apples first, which helps maximize the number of apples we can fit within the weight limit. Next, we initialize two variables, total weight to track the cumulative weight of the apples added to the basket, and count to track the number of apples included. Then, we use a for loop to iterate through the sorted weights. For each weight, we check if adding it to the current total would exceed the weight limit of 5,000 grams. If it does, we exit the loop using break. Otherwise, we add the current weight to total weight and increment the count. Finally, the method returns the total count of apples that can fit within the weight limit. In this slide, we have the main method, which demonstrates how to use the solution class and the maxNumberOfApples method. We start by creating an instance of the solution class. Then, we define an array called weights, which contains the weights of the apples we want to process. In this example, the array includes values of 100, 200, 150, and 1000 grams. We then call the maxNumberOfApples method on the solution instance, passing the weights array as an argument. The result of this method call, which is the maximum number of apples that can fit within the 5,000 gram weight limit, is printed to the console using system.out.println. This example shows how the method works with a sample input, and you can use similar code to test the solution with different arrays of weights. To solve this problem, we start by looking at an example where the input weights are 100, 200, 150, 1000. The first step is to sort these weights in ascending order to make it easier to efficiently pick the heaviest combination of apples that still fits within the weight limit. After sorting, the weights become 100, 150, 200, 1000. We then initialize two variables, total_weight to keep track of the cumulative weight of apples added to the basket, and count to count the number of apples in the basket. Both are initially set to 0. In the first iteration, we take the weight 100. Adding it to our current total gives us 100, which is less than or equal to 5,000, so we proceed. We update total_weight to 100 and increment count to 1. In the second iteration, we take the next weight, 150. Adding it to our current total of 100 gives 250, which is still within the limit. So again, we proceed, updating total_weight to 250 and count to 2. In the third iteration, we move to the weight 200. Adding this to our current total of 250 gives 450, which is still less than or equal to 5,000. So, we update total_weight to 450 and increase count to 3. Next, we consider the weight 1000. Adding this to our current total of 450 results in 1450, which is still within the limit. We proceed by updating total_weight to 1450 and count to 4. Since there are no more weights to consider, the final output for this example is count equals 4, meaning we can fit 4 apples into the basket without exceeding the weight limit. Now, let's consider a second example where the input weights are 900, 950, 800, 1000, 700. Again, we start by sorting these weights in ascending order, which gives 700, 800, 900, 950, 1000. We initialize total_weight to 0 and count to 0. In the first iteration, we pick the weight 700. Adding it to our current total of 0 gives 700, which is within the weight limit. So, we update total_weight to 700 and increment count to 1. In the second iteration, we take the weight 800. Adding this to our current total of 700 results in 1500, which is still less than or equal to 5,000. We proceed by updating total_weight to 1500 and increasing count to 2. In the third iteration, we pick the next weight, 900. Adding this to our current total of 1500 gives 2400, which is within the limit. We update total_weight to 2400 and increment count to 3. Next, we consider the weight 950. Adding this to our current total of 2400 results in 3350, which is still within the weight limit. We proceed by updating total_weight to 3350 and count to 4. Finally, we take the weight 1000. Adding this to our current total of 3350 gives 4350, which is still less than or equal to 5000. We update total_weight to 4350 and count to 5. Since all the weights have been processed, the final output for this example is count equals 5, meaning we can fit 5 apples into the basket. In the third example, the input weights are 4000, 3000, 2000, 1000. After sorting them in ascending order, we get 1000, 2000, 3000, 4000. As usual, we initialize total_weight to 0 and count to 0. In the first iteration, we pick the weight 1000. Adding it to our total of 0 gives 1000, which is within the weight limit. We proceed by updating total_weight to 1000 and incrementing count to 1. In the second iteration, we take the weight 2000. Adding this to our current total of 1000 results in 3000, which is still less than or equal to 5000. We update total_weight to 3000 and increase count to 2. Next, we consider the weight 3000. Adding this to our current total of 3000 gives 6000, which exceeds the weight limit. At this point, we stop processing further weights. Since no more weights can be added without exceeding the weight limit, the final output for this example is count equals 2. This means we can only fit 2 apples into the basket without going over the weight restriction. By sorting the weights and iterating through them in ascending order, we ensure that we maximize the number of apples that can fit within the given limit, as demonstrated in all 3 examples. To analyze the time complexity of this solution, we start with the sorting step. When we sort the list of apple weights using Python's timsort algorithm, the time complexity is O, n log n, where n is the number of elements in the list. This is because timsort is highly efficient and guarantees this performance across all cases: best, worst, and average. Once the list is sorted, we then iterate through the weights using a for loop. In the worst case, we might need to process all n elements if the combined weight stays under 5,000 until the final apple. Each iteration involves simple operations like comparison, addition, and increment, all of which are constant time operations, so this step contributes O, n, to the time complexity. When we combine these 2 steps, the sorting step, O, n log n, dominates the linear iteration step, O, n. As a result, the overall time complexity of this solution is O, n log n. Now let's examine the space complexity. The input list of weights itself takes up O, n, space since it contains n elements. For the sorting step, Python's timsort is an in-place algorithm, meaning it does not require extra space to create a new sorted list. However, it does use a small, constant amount of auxiliary space for temporary variables, which is O1. Additionally, our algorithm only uses a few extra variables, such as total underscore weight and count, which also require O1 space. When we add these together, the total space complexity becomes O(n) for the input list, with the additional constant space being negligible in comparison. Therefore, the overall space complexity of the solution is O(n). Let's compare this optimized solution to a brute force approach. A naive method might involve generating all possible subsets of apples, calculating the total weight for each subset, and checking if it stays under 5,000. Since there are 2 to the power of n subsets, and summing the weights of each subset takes O(n), the time complexity of this approach would be O(2 to the power of n asterisk n). The space complexity would also be O(2 to the power of n), as we would need to store all these subsets. In contrast, the current solution avoids the exponential growth in both time and space. By sorting the weights in O(n log n) and iterating through them in O(n), we achieve a much more efficient time complexity of O(n log n). Furthermore, the space complexity is reduced to O(n), as we only store the input list and a few simple variables. Clearly, the optimized approach is significantly better for large inputs. Finally, let's consider the best, average, and worst cases for this algorithm. In the best case, the total weight of the apples exceeds 5,000 early in the iteration, perhaps after just a few apples if they are particularly heavy. Here, the loop terminates quickly, and the time complexity is dominated by the sorting step, resulting in O(n log n). In the average case, the loop processes a moderate portion of the list before hitting the weight limit. Even so, the overall time complexity remains O(n log n), as the linear iteration does not change the asymptotic behavior. For the worst case, where no weight exceeds 5,000, the loop processes all n elements. However, even this scenario does not change the overall complexity because sorting, which is O(n log n), still dominates the O(n) iteration. Mathematically, O(n log n) plus O(n) simplifies to O(n log n). Therefore, in all cases, the time complexity is O(n log n), and the space complexity remains O(n). When solving this problem, there are several common mistakes to watch out for. First, a frequent error is not generating all possible subsets of apples in a brute force approach. This happens when only a few combinations are tested, which can lead to missing valid solutions. To ensure completeness, you can use techniques like bit masking or recursion to systematically explore all subsets. Another common oversight is failing to check if the total weight of a subset exceeds the weight limit, which is 5,000 in this problem. This validation is critical and should be integrated into your logic. Additionally, inefficient handling of weight calculations can hurt performance. Instead of recalculating the total weight of subsets repeatedly, consider using optimizations like prefix sums or maintaining a running total to save computation time. Finally, don't overlook edge cases, such as the empty subset or subsets that exactly match the weight limit. These scenarios can lead to incorrect answers if not handled explicitly. And, of course, remember to analyze the time complexity of your approach accurately. For example, generating all subsets has a time complexity of 2 to the power of n, which becomes impractical for large inputs. Being mindful of these details will help you avoid common pitfalls. Now, this problem has strong parallels with the knapsack problem, where you need to balance between the total weight and the total value, which in this case is the number of apples. Interviewers often focus on how you optimize the brute force solution, so it's important to demonstrate your thought process clearly. One effective strategy is to introduce dynamic programming as an alternative. This drastically reduces the time complexity for problems like these, making it a valuable optimization to discuss. Additionally, recognizing patterns such as the subset sum or knapsack structure in this problem can be a key insight. These patterns are common in algorithmic interviews, and they often involve techniques like recursion or dynamic programming. Finally, it's crucial to explain the trade-offs between different approaches. For instance, you might compare the brute force solution with its exponential complexity to the optimized dynamic programming approach, which has a complexity of n*w, where w is the weight limit. Be prepared to discuss how these solutions differ in terms of time and space efficiency. There are also several related problems that you can study to deepen your understanding. For example, LeetCode 416, partition equals subset sum, is a classic problem that involves finding subsets with equal total values and uses similar subset exploration techniques. Another relevant problem is LeetCode 322, coin change, which also involves optimization under constraints, but focuses on minimizing the number of coins required instead of maximizing the count of items. LeetCode 494, target sum, is another great example, as it involves assigning signs to numbers to reach a target sum, which is conceptually similar to subset-related logic. Finally, while LeetCode 674, longest continuous increasing subsequence, may seem different at first glance, it shares a focus on dynamic programming optimization strategies, making it a useful problem to practice. Exploring these problems will not only reinforce the concepts but also help you recognize patterns more effectively in interviews. To solve this problem, you can consider alternative approaches, each with its own trade-offs. Dynamic programming is a powerful option where you use a DP table, with dp, w, representing the maximum number of apples that can be picked without exceeding weight w. This approach significantly reduces the time complexity to n*w, but it does come at the cost of increased space usage, which is w. For cases with large weight limits, additional optimizations may be necessary. Another approach is backtracking with pruning, where you use recursion to explore subsets but prune paths where the weight exceeds the limit. While more efficient than brute force, backtracking is still exponential in the worst case, so it's best suited for smaller inputs. Finally, a greedy approach can be applied in some scenarios by sorting the apples based on weight or count and picking items until the weight limit is reached. This method is fast, with a time complexity of n log n for sorting, but it doesn't guarantee the optimal solution in all cases. Understanding when to use each approach and the trade-offs involved will help you tailor your solution to the specific requirements of the problem. Great work! In this session, we reviewed the how many apples can you put into the basket problem and examined the brute force approach. Remember, problem solving is about clarity, efficiency, and adaptability. Don't forget to practice similar problems to strengthen your skills. Thanks for joining, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!